Alright, so in class we solved the Schrodinger equation for a free particle using the separation of variables method, and we got this solution where E is equal to p squared divided by 2m, and p runs from minus infinity to plus infinity. And we showed that this solution has a few problems. The first is that the velocity of the particle does not, the velocity of this wave does not seem to match the velocity of the particle. We'll deal with that later. But another problem is that this is not normalizable. So if you calculate integral psi star psi, then the exponential factors are going to cancel out and you're just going to be left with dx. You're just going to be left with integral a square dx, and you're integrating from minus infinity to plus infinity, and so that would just be infinite, so that diverges, and so that's a problem. But then I claimed that if you form the most general solution, that will not diverge. Now what do I mean by that? Notice that this solution is for a particular p, because the E also depends on p. So this solution really is for a particular p, and I should strictly label it as psi of p, because this is a solution for one particular p. For a different p, I'm going to get a different solution. The p value will be different, p number will be different in that. So there's an infinite number of solutions, one for each p, since p runs from minus infinity to plus infinity. Now the most general solution can be obtained by superimposing or superposing these solutions for each p. Now why is that? We've discussed in class that the Schrodinger equation is a linear equation. So I h bar del psi del t is equal to h times psi, h being the Hamiltonian operator. Now this is a linear differential equation, which means that if psi 1 is a solution and psi 2 is another solution, if psi 1 and psi 2 are solutions, then a linear combination, so a1 times psi 1 plus a2 times psi 2, and if you have more than a3 times psi 3, if you linearly combine all these solutions and call that psi, this psi will also be a solution. Also a solution. That is called the linearity property of the Schrodinger equation. It's a property of any linear differential equation. You can easily plug this psi in, and you will see that as long as psi 1 and psi 2 are solutions, then this linear combination where I've taken psi 1 and psi 2, multiplied them by constants and added them, is also a solution. So since the Schrodinger equation is linear and has multiple solutions, the most general solution is obtained by as a linear superposition of all the solutions of the Schrodinger equation. But what do you do if you have an infinite number of solutions? For a finite number of solutions, I can add them up. I can multiply each one by a constant and add them up. For an infinite number of solutions where it's continuous, where the solutions are labeled by this continuous variable p, then the idea is the same. Psi xt, and this is the most general solution, is going to be an integral, not a sum of, you take each psi p, multiply it by a number, and that number depends on p. That's why I'm writing it as a function of p. That's analogous to the a1, a2 that I was writing. And instead of summing, you take an integral over all p. So that's the analog of, if I had a certain number of discrete solutions, then I would do a1 psi 1 plus a2 psi 2 plus a3 psi 3 and add them all up. Here I have an infinite number of solutions, one for each p. So for each solution, I'm multiplying it by a constant, and that constant depends on the p. And so a of p psi p, and then I'm integrating rather than summing because it's continuous. and p's run from minus infinity to plus infinity. So this integral goes from minus infinity to plus infinity. So this is the most general solution. And I'm claiming that this most general solution is going to be normalizable. And so let me just write this again. Psi of xt is equal to, and I'll just plug in the what I had for psi p, a, and I'll take the a outside. Actually, I can take the a completely outside of the integral. A of p e to the power of I over h bar px minus et dp. So all I did here was just put down what the psi p is. Okay, so what I'm claiming is psi most general solution xt, psi star xt, psi xt. If I integrate this from minus infinity to plus infinity, the result will be equal to 1. And we will see that this result will be equal to 1 indeed if we choose a is equal to 1 over square root of 2 pi h bar, and also if a of p is normalizable. So that means if a p square dp minus infinity to plus infinity is equal to 1, then this quantity, this will be true. And this is exactly what we want. We want our solution, for our most general solution, to be normalizable because it represents a physical particle. All right, so how do we prove this quantity inside my weird box here? So in order to prove that, and this is integral over dx, not dp. Okay, so in order to prove this, we will just directly calculate it. So what I'm going to do is I'm going to have the outermost integral, which is over x, and then I'm going to plug in the psi star x. So I'm going to take the a completely out of the integral, so I'm going to write that as a star because I'm doing psi star right now. And then I'm within square brackets, I'm going to put in the first integral, minus infinity to plus infinity, a star of p e to the power of minus I over h bar px minus et dp. Now I'm going to make one change before I proceed further, which is not that change, okay, which is I'm going to express the e in terms of p as well, just so it's clear that p, everything depends on p here. Okay, and one more thing that I'm going to do is I'm going to change, I can call this dummy variable, this I'm integrating over p from minus infinity to plus infinity, so p is a dummy variable. I can call it whatever I want. So to avoid confusion, because I'm going to have another p in a moment, I'm going to call all these p's inside these square brackets as p prime. Alright, so I just relabeled this dummy variable. Now I'm going to take the psi. So this was the psi star. This was the psi star. Now I'm going to take the psi. Okay, so it's going to give me a factor of a, which I'm going to take all the way outside here, and then integral from minus infinity to plus infinity. This integral is over dp, and a function of p, e to the power of I over h bar px minus et dp. And then there is the overall integral over integral dx. All right, so this is what we need to evaluate right now. There are three integrals here. Okay, so a star a is just absolute value of a squared. So now let's write the first integral. I have minus infinity to plus infinity. Let's write the, so you can, since these variables are all independent, you can have the you can rearrange the order of the integrations. So what I'm going to do is I'm going to keep the p prime integral first outside. So I have a star p prime, and I'm going to bring the a of p integral here as well. I mean a of p quantity over here. So I'm mixing up everything inside the integrand because they're independent variables. So there's no problem in mixing them up. So I have the a star p prime, a of p. Okay, then let's bring in this term and this term. And here I'll replace this e also by p squared divided by 2m. Okay, so what we have is e to the power of I over h bar p prime square. Let me just factor out the 2m as well. I over 2m h bar p prime square minus and then the second term that I'm bringing in, which I've underlined in blue. So that's going to be I over h bar 2m p squared t. Okay, so I brought in the two terms that I underlined. All right. Okay, now what am I left with? I'm left with e to the power of I over h bar p minus px, p minus p prime times x. So now I'm combining this term and this term. Okay, I'll just keep the h bar inside. You'll see why in a moment. X. Okay, so I brought in these two terms. All right, now what? Now I need to put in all the integrals. So I'm going to keep the p and p prime integrals outside. So one of them is p prime and the other one is p. And I'm going to have a dp prime dp. There is still the x integral. So what I'm going to do is I'm going to do the x integral first. So I'm going to put it over here. I'm integrating x equals minus infinity to plus infinity, and I'm going to put the dx right here. So essentially I just rearranged the order of the integrals and put a square bracket around this. Oops. Square bracket like this. Okay, now that I do this, you can immediately recognize what this is. This is nothing but delta of p minus p prime divided by h bar. Okay, now delta of p minus p prime, and it's 2 pi times delta p minus p prime over h bar. So this is the integral representation of the delta function. So just take a look at the integral representation of the delta function formula, and you will see that this is exactly what that is. Now there is a property of a delta function that if you divide the argument of the delta function by a constant, then and I'll just write it, I might as well just write it over here, delta of p minus p prime over h bar is just going to be, or over any constant, let's call that c, is going to be c times delta p minus p prime. That's a property of the delta function. So that means I'm going to have a factor of, so this can be written as h bar times 2 pi delta p minus p prime. That's what that is. So, okay, and yeah. So if I plug that in, that is actually a huge simplification. Minus infinity to plus infinity, minus infinity to plus infinity. So these are the p and the p prime integrals. A star p prime, a of p, e to the power of I divided by 2m h bar, p prime square minus p square t, and then 2 pi h bar. So I'll just bring the 2 pi h bar outside. Delta of p minus p prime dp prime dp. All right, so now I'm going to use the shifting property of the delta function. So if I have some function f of p prime and then I do multiply it by delta p minus p prime and dp prime and integrate p prime equals minus infinity to plus infinity, what is the result going to be? It means that whatever I have outside of the delta function, in this f of p prime, I just need to replace the p prime by p. So this is going to be f of p. This is the shifting function, the shifting property of the delta function. So that's what I'm going to do. I'm going to integrate over dp prime, which means everything here where I have a p prime, everything in here, wherever I have a p prime, it becomes p. So if this p prime becomes a p, if this p prime becomes a p, then I get e to the power of 0, which is 1. And so I have 2 pi h bar absolute value of a square. Now I'm only left with the integral over p because I'm done with the integral over p prime. I'm going to replace the a star p prime by just a star p. So everywhere I see a p prime, I just replace it by a p. And as I said, in the exponential factor, when I replace the p prime by p, the whole thing just disappears. So I'm left with a star p, a of p, dp. That's all that I'm left with. And now I can just write this as 2 pi h bar integral over p, that's the only integral I'm left with, a star p to a of p, so that's a of p absolute value square dp. That's the result when I evaluate this quantity inside the box. So if this a of p is normalizable, so I mean if this quantity is normalizable, oh, and I forgot the a absolute value of a square, 2 pi h bar absolute value of a square. So if this quantity inside my yellow boundary is normalizable, and we'll see that it is, then this quantity just needs to be equal to 1 in order for the whole thing to be equal to 1. So I'm claiming that this will be equal to 1, and if I can just make this equal to 1, then the whole thing becomes equal to 1. And so in order for this to be equal to 1, I need a square, absolute value of a square is equal to 1 over 2 pi h bar, or in other words, a is equal to 1 over square root of 2 pi h bar. Okay, so then the whole thing will be normalizable. And so the normalized most general solution, psi star x t, most general solution is going to be 1 over 2 pi h bar, square root of 2 pi h bar, e to the power of what I had over here, integral minus infinity to plus infinity, a of p, e to the power of I px minus et, and e being p square over 2m dp. This is the normalized most general solution. In the next class, we will see how the initial value, the value of psi, oh, why did I put the psi star here? The initial value, psi of x t equals 0, is what determines a of p. We'll see that in the next class.